Good evening. Welcome to the week 12 of Fundamentals of Additive Light Manufacturing. So, today we will discuss on electron beam melting additive manufacturing. So, let's start the class and okay, we will begin. Now, in an electron beam melting additive manufacturing. So, this is the schematic you are seeing of electron beam additive manufacturing, and this is the magnified view. Okay. Now, okay. So, few of the questions from assignment related to the electron beam additive manufacturing process. So, this is the we'll study the basic mechanism behind this, and some related to schematic we have also studied in the last class. So, first we are seeing the filament. Now, this filament is enclosed in the electron gun. Filament is enclosed in electron gun. This filament is made up of tungsten. Now, enclosed in electron gun using tungsten made up of tungsten using because of melting point is very high. T melting is 3422 degrees Celsius. So we provide a temperature input of around 2500 to 3000 Celsius input temperature. So because of this filament, electron emission will take place. Now this filament will focus on form of electron beam and strike the particles and increase the temperature and help us to build the layers in the form of beads. This is the mechanism for electron beam melting additive manufacturing. I'll again repeat that this beam will hit the powder. This temperature will be created in the filament. It will strike the beam, and layers will be created in the form of beads. Okay, so here we are using the electron beam, and it is similar to the laser beam also. Difference is that here we are using electron beam and we are creating a vacuum. See, so here we have a vacuum changer. In laser we do not have a vacuum. Now the other thing is anode, and from the anode electrons move towards the cathode. Now focusing element is there, which we have already discussed, like magnetic coil, focus coil, deflection coil. This has to convert electron beam. So this is okay. Till now nothing was audible. Okay, I'm sorry. You should have interrupted me. Wait, I'll melting process. It is similar to the laser beam also, but only difference is here we are creating using electron beam and creating a vacuum. In laser we do not have a vacuum. So other thing which you can see here is the anode, and from the anode you have the anode here. So it's anode, electrons are moving towards the cathode. Some focusing elements are there, focus coil, deflection coil. We have already discussed in magnetic coils are there. This helps us to converts the electron beam uh, due to the one question is there in assignment, due to the negative charge. Suppose this is the beam, this is the beam, and all these electrons are having negative charge, negative negative will start to repel each other. So when it is starting, this d minimum is very small. As it travels towards the powder particles, at this point the diameter increases and again it narrows down. Why this is happening is because of the repulsive forces here. Repulsive forces between the electrons. Now what it will do in the laser beam, we can see that it is a possible to maintain a laser spot or beam radius. Okay, or beam radius, that is in laser spot or beam radius at but in case of electron beam it is not possible. So so the spot size is here, but here it is not possible. The spot size is around 100 to 150 micron because of this electron repulsion. So the problem, when we use such size, the surface finish of the final reviewed component will be higher than as compared to the laser beam additive manufacturing process. So this is some question is there in the assignment. Now here we have a powder container and we are using a preheating. Now this is your powder bed. Now preheating, we supply the heat in two steps. Heat in two steps. First is we use low power density electron beam. So we control the low power electron density by adjusting beam current, scan rate or beam focus. So by changing these we can change the electron beam power. Okay, we can change the electron beam power. So in preheating we have to only heat it, we do not melt it, because if we melt it in the first stage, suppose this is our consider this as the powder bed. Okay, if in a component, consider the top layer is like this. So in the preheating stage, we are not heating the entire area. This entire area will be heated. We are not focusing only on this area, but our shape of the component is only this area. So melting should take place only at this portion. So if we increase the preheating area, ultimately this whole entire thing will get centered. So this will be difficult and result in difficulty of removing the component. So all the powder particles adjacent to the component will be destroyed. We cannot. We have to optimize the preheating temperature carefully based on your material. And this parameter helps in changing the we can adjust the preheating temperature. Now second stage is of preheating is we use the focused beam melting. In this stage actual printing takes place. Other benefit of using the preheating is reduces powder smoking. Now this term I will tell you just little bit later. Oh, so this is a this a problem is always there in electron beam, but we'll discuss this problem. We can avoid this problem, but we cannot completely remove this problem. Now preheating also conductivity, increases conductivity. Now other benefit is it reduces thermal gradient. Now thermal gradient is we are building this component and here printing takes place. When we are building an aluminum component, the temperature at this point may be 1000 degrees Celsius. Now base plate is at 100 degrees Celsius. Now we can see the difference of 900 degrees Celsius. This is thermal gradient. This will create residual stresses. Reduce the mechanical strength of a component. So that is why we use preheating, as thermal gradient will reduce and the final product will be of a good quality. Now next we will discuss this. Now here this is the beam, okay, the enlarged view of a tray. There is a question related to this also. So question is that what is the objective distance and image distance? So now distance between the anode, and we will take the distance between and the radius of the radius. So here we will draw one more figure here, this and this distance. So this is known as your objective distance, okay, and this is the distance from the minimum diameter to maximum diameter, again from the maximum diameter to the uh, this distance, image distance. So this is the difference between the objective distance and the image distance. A question is there related to this, okay. Now next we will go to discuss about powder smoking, okay. I think I missed the slide. Now I'll just paste that slide, bring that slide. Yeah. So we were talking about powder smoking. So this is a normal. This is normal when there is no normal electron beam. In the second, this is normal. Now here we can see electron beam is coming. Okay. Now the speed of the electron beam is 2 by 3 times of velocity of light. It is very high speed. Now we have the powder particles here. Ultimately, the electron is lying on the powder particles, and it will transfer all the kinetic energy to the powder particles. Okay, this will transfer all the kinetic energy to the particles. So one of the reason is that it will scatter. So powder smoking is scattering of powder under electron beam irradiation. So ultimately it will look like a smoke. This is the smoke. That is why it is known as powder smoking. So velocity is not the only main reason why this happens. Main reason is the electronegativity of the powder particles. What it will do is electronegativity of the powder particles Suppose we have this powder particles. Now these powder particles are made with different process like gas automation. Okay, in gas automation we will melt the material, and we pass the molten material to the nozzle, and because of the air the molten material is getting converted into a powder particles. So these powder particles are in contact with the air, so this forms some type of oxidation layer. Okay, so suppose this is a powder particle and this is a layer, so you can see there will be a oxidation layer. This is the oxidation layer. So this oxidation is your oxidation layer. This is not conductive. Powder particle is conductive, and the powder in electron beam process, the powder should be conductive. So this oxidation, when the electron is coming like this, what they will do, they will hit the try to get inside this oxidation layer. Okay, so they will get trapped because outside layer is insulated. This is not conductive. This insulation will prevent the transfer of negative charge to the powder particles. Prevent transfer of negative charge to the powder particles. So ultimately, so your powder particle inside will remain with a negative charge because the electron is stored in the powder particle. So before the powder particle was neutral, there was no charge, but now it has a negative charge. Okay. Now the adjacent particle, again electron will trap. Ultimately, this will create a cloud of negative charge because each trapped particle will be having a negative charge. Now before, the problem was only with the beam. Beam in the electron was having the negative charge, but the powder particle is also negatively charged. What they will travel to do? They will try to repel each other. Okay. So when they try to repel each other, this powder smoking will take place. So there is a method by which we can reduce this type of problem. So that depends on the how we are spreading your powder, methods to reduce powder smoking. How powder is being spread. Okay, this is very important. Now powder smoking has synonyms such as powder pushing, powder blowing. So this problem can be reduced by preheating. Powder pushing, powder blowing, preheating. Preheating will help us to remove the air. This powder smoking, this air. Air, okay. Preheating helps to reduce powder smoke. So I think there is a question related to this, how this occurs due to transfer of negative charge. Okay. How this occurs? How occurs due to negative transfer of negative charge electron particles to the powder particles. Due to transfer of negative so one more method, some other methods are also there. Based on the methods, there is some question that how do we reduce to, why do we use hybrid powder particles? Okay.
So, do we also call it as electrostatic charge?
Yes, you can. To what you are saying you will call electrostatic charge?
So, the negative charge which is there
Mm-hmm.
on the powder particle will cause
Okay. Yes, yes,
major line and so just allow the field effect.
yeah, yes. Mm, uh, not exactly. Somewhat. Not exactly. Where was I? Yeah. This occurs due to transfer of negative charge electron to powder particles. I think that option, is it related to your assignment?
Yes, yes.
Okay, okay. Okay. So this is the powder hybrid. When we talk about hybrid powder particles, so what it will do is hybrid powder particles. This is a combination of smaller and larger bigger size particles. Okay. Now it will improve packed density. Now powder is getting scattered because of the electron beam. So if we increase the size of the powder particles, or if, like, suppose we are using 50 micron and we are using 200 or 300 micron powder particle size, problem is that if we use a very big particle size, ultimately the surface roughness surface roughness of a final product will be very high. So that is why we use hybrid particles. So this will improve the pack density. Improve pack density, I have written here. So if the powder particles will be packed, it will not take this. It will also increase finally your conductivity. Now, before we were also seeing that we have, because because of this oxidation layer, it was not possible to transfer the heat from one particle to another. If we can use the combination of smaller and bigger particles, it will be transfer the heat from charge or heat from one particle to other particle. It won't be trapped inside one each layer. The heat can be transferred to the other particles. I think someone has left their mic on. Can you please mute it off? So next is we are going to. I hope you had your doubt cleared. Electrostatic is the reason. Okay.
Clear.
Yeah, yeah. So now one more thing is, we if we are using a preheated layer also here, we won't face warping in EBM. We won't face warping in EBM process. Okay, so preheating is very important in your no warping. Okay. Now few questions are related to your powder manufacturing method. So we have powder manufacturing routes like pulverization, electrolysis, gas automation, plasma automation. So these are some of the common methods which are used in the production for the powder. okay, which are being, these are commercialized, commercial, okay. First is pulverization. Now pulverization means we take two bigger particles and crush it. This is like similar to your ball milling. Now this is ball mill and shaker mill. We take two particles and we crush it. Okay. So here like ball mill and shaker mill which you are seeing, it is in rotating, rotary motion. So bigger particles will be converted to the smaller particles. But the problem is we cannot control the shape of the powder particles. No, not possible to control shape. Now in the 3D printing process, we are generally preferring spherical particles. There are some studies where we use non-spherical particles, but those are not commercialized till now. So for now, our requirement is that we need to use spherical particles. If we use this pulverization method, we cannot have a control whether it will be the particles will be spherical upon breaking. Okay. So that now, suppose if you take a brass powder particle of powder particle that's the size of 15 micrometer, so we tried to reduce the size to some nanometer, but we could not. So maximum range can be achieved to 50-60 nanometer. Okay. Next is electrolysis. So electrolysis is nothing. This is the electrochemical, similar to electrochemical machining. So electrolysis is also being used these days. Here we have an anode, anodic solution. So if you want to make a copper and aluminium powder particles, okay. So we have to use aluminium as a anode and cathode will be, other material will be taken. By supplying suitable potential, this anode will start to dissolve. Now because of this process we can get very pure powder particles, but for the problem for this process is that we if we so when we are trying to machine some alloys, it will be not easily machinable because they are combination of different because this is a combination of different materials. So dissolve like titanium, aluminium, different 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 potential is required to dissolve each material. So for when this alloy is there, when each time different potential will be required, it will be difficult to dissolve it. So if a material is single, this is single element like copper or aluminium, then it is we can dissolve it. But for aluminium, but for aluminium powder particles, we cannot use this process. Now, this is the gas atomization is the most common process. If you are using gas, it is called as gas automation. When using plasma, it is a plasma atomization. Okay. Now here, what happens is when molten material is coming from sides and there is a jet of air. Okay, this there will be a jet of air. I have not shown the image. This air will convert the powder particles and there is a sieve below this that will distribute the powder particles according to their size. This process takes place in this way. Now some other processes are also there. There are laboratory scale in our so like electrode micro electrode discharge machining process. Okay, so so but these are not fully commercialized. Okay, so next we will move on. Next, so this side is repeated. So this is the problem in EBM process, and what are the problems and how it is compared with other laser based processes. First problem is martensite microstructure. uh, so problems we have already discussed. One is powder smoking. This is very important, you should remember this powder smoking method. Second is needs vacuum requirement. So this will create a costly method. Now laser beam, we can get commercialized laser beam at manufacturing, it will be 50 lakhs, but electron beam will be costlier. Now only electrical conductive powder particles can be used. Non-conductive ceramic plastic cannot be used. Now if the electrical conductivity is less, then also we can not use, only high conductive material should be used. Now uh, now one more thing is life of the laser. We derived the question life of the laser. It was some, the life was around okay, life 12 years or something. So electron beam gun doesn't have that much life. Low life of electron gun. So if we compare 3D printing processes, SLM selective laser melting, EBM conventional manufacturing process, casting, forging, so best mechanical properties we get with SLM. Superior mechanical strength. EBM is high, it is good. Okay, so this is a decreasing, you are seeing. Okay, the SLM is always superior in most things. Suppose it is 1000, it is 900, it will be 700. Okay, now 3D printing components always have higher elastic modulus of stiffness as compared to your forging for conventional manufacturing processes. But the problem is the ductility. Because of residual stresses, ductility is not very high here. In the SLM process, we have a low ductility. Average. good ductility. Now, suppose let's take an aluminium testing tensile testing sample. So, uh, so suppose aluminium tensile testing. So here they will break after 15 to 16% of strain. But in SLM and here they will break at 5 or 6 percentage only. Okay. So EBM process has higher ductility as compared to SLM because in EBM the whole system is packed in vacuum. But in powder and your powder bed is preheated, but your residual phase is lower as compared to the SLM process. So this is the reason behind the higher ductility in EBM as compared to SLM. Now, about talking about the microstructure. So here we have three different types of microstructure: martensite, Vince-Martin, and bimotor microstructure. Now in SLM we have so I hope you must have heard this martensite name, but I'll explain. This vid this is Widmanstätten microstructure, and here we have bimodal microstructure. Okay. Now because of these so your microstructures define your ductility depends on your microstructure. Okay. So now we'll understand what all this microstructure. So this microstructure looks like this. Okay. So like in a regular smith shop, they will put some hammer, and then after the forging, he the heated hammer they will put in the water. A lot of smoke will come. So when we use that type of structure, you will get this martensite of puck. This is happening because of higher thermal gradient. Now, when your cooling rate is very high, we get this type of microstructure. In EBM, powder bed is heated, so usually we cooling rate is not that much high as compared to the SLM process. So we will get this type of microstructure. That name is Widmanstätten microstructure, named after this person. He discovered this type of microstructure. Okay. Now this type of microstructure is mostly available uh, iron ore extract or asteroid. Yeah. Hmm. Now this is the maximum higher ductility we get. Here the grain size is very. Now let's consider this is Ti6Al4V. Now this is a bimodal microstructure. As we can say, this is alpha beta. Now here the grain size is very small. Now benefit of the first two is that hardness and modulus values are is much higher than the conventional process. So based on the application of your product, we can select which type of process we want to use, SLM, EBM or conventional. If okay, suppose if we go with a stress strain curve, this is a normal stress strain curve of a mild state. Okay, if the product is only in this range throughout its life, then the amount of load or stress is throughout in this range only. If it is not going above that, so in those processes we can use 3D printing efficiently. Okay, but if your component is crossing near the yield point, okay, after the yield point we will not talk because ultimately the load is will fail. So if the if this is, suppose this is the lead point, and if it is a fatigue type of loading, cyclic loading, so even after that also your product will fail. So if the amount of deformation which you experience in a component is high, then we can use the bimodal microstructure or conventional methods. Here, in this case, we can use conventional methods. So, but if your component is not having much deformation, then we can use your other two processes. Okay. Now, with single heat we have to use other heat uh, we have to use single heat treatment process also for this to give this type of microstructure. Okay, from 3D printed also we can get this type of microstructure by using single different types of heat treatment process. Okay, now based on the designer, now in terms of ductility only we can say bimodal structure is the best one. Now in terms of ductility, how much we can ductility means how much we can stretch with before the failure. But if we talk about stiffness, but for stiffness, hardness 3D printing is best. So design is the finally functionally graded or some different assemble different components or different components. So for only for the design of prototype, then you can use you must use 3D printing process. Okay. Okay. So when you are doing something with your design or internal structure or functionally graded, or you're doing some complicated, then you should use your 3D printing process. But other things for your, like suppose if you are doing a gen generally structure, then like we are trying to make a plate or a bowl normal thing, we should use the conventional because cost will be less for mass production. For mass production process, never 3D printing is good. Okay, so this was about some the concepts to be covered today. Okay, I have some questions. We'll quickly go through those questions. these are the questions. So the first question is, okay, which of the following materials, some basic questions, which of the following materials can be used as aqueous inks for binding component in powder for binder based powder bed manufacturing? Now this is solventing polyactide. We use solventings. Polycaprolactone is also solventings. So our correct option, this is a straightforward question. So this is this. Now this and starch and ionomer cements. Now materials for, I am writing this as BPBAM, boundary based powder additive manufacturing method. So here aqueous inks means you have starch, cellulose, plaster and ionomer components, cements. So for this we have ink and powder, and this powder is again as solvent ink and aqueous ink. This is the division. So here your correct options are ionomer cements and polycaprolactone. Now your next question is, now we are discussing a little bit on powder binder based powder bed additive manufacturing. Which of the following are correct statements for binder based powder additive manufacturing? Wide choice of powder and binder possible? Yes, this is correct. Binder based powder bed manufacturing can exercise control over local material composition. This is also correct. They have unique facility. This is also correct. So correct option is all of the above. So what is the unique flexibility here? Now the unique flexibility is binder can be mixed with other materials. That means this is a very important point. Now this has control over composition, microstructure and surface texture. Okay, now we'll go quickly to the next question. Which of the following are characteristics of piezoelectric head in binder based powder bed additive manufacturing method? Now there are two types of head, piezoelectric head and thermal head. Now piezoelectric head and thermal head. The thermal head has, now the correct characteristics of piezoelectric head are your relatively low printing speed, high droplet directionality, high cost. Thermal head has non-uniform droplet size. Now some other characteristics of piezoelectric head are, it has a high cost, there is no thermal exposure and high droplet directionality. High cost, no thermal exposure. Now next question. In binder based powder bed additive manufacturing, which is correct with respect to support structure? Now we need to understand that there is no explicit support structures are not required in this type of method, piezoelectric head. Now, when a binder is sprayed on a selected region, the particles in the region stick together and the remaining powder acts as support. So, we do not need any explicit support structures in binder bed at AM processes. And also, loose powders act as support structures. Okay. So, the next question. In the continuous nozzles for dispensing ink in the powder bed binder based powder bed additive manufacturing, why is the deflection of the ink stream done? Now, suppose this is the nozzle. Now, this should be the correct path, but here we do a deflection. Okay. Now, there is a droplet and it is the ejection path is there. This is the deflection path. This is the droplet and this is the substrate. Now, this deflection is carried out by applying an electric field. Okay. Now, this is done so as to completely stop the flowing is difficult to achieve. So that is why the stream is deflected from its path, and it also provides selective deposition of the ink on print bed. So the correct option is all of the above, but it is not used for drop on demand dispensing of ink. It is only carried out by applying an electric field. This deflection carried out by applying an electric field, and it is not used. This is the nozzle. It is not used for drop on demand dispersing of ink. Okay. Now the next question. Why binder based powder bed additive manufacturing is suitable process for producing time delivery drugs? Now, as we saw, the process dispenses material from two different sources. Deposition process is having the ability to control flow rate of multiple materials. So, with some particular conditions, we can also vary the diameter. So, when we can control the flow rate in such methods, we can control flow rate of multiple materials. So what is having the control flow rate? Like deposition process is having the ability to control the flow rate of multiple. So with this, because as we can control the flow rate of different multiple materials, we can use different sources for dispersing materials. Dispensing materials. So it is used in pharmaceutical areas. Okay. Now, this type of Z-Corp 3D printer you must have seen in slides. So, which of the following statements are correct? So, this was a this is the type of thing where you have to require remember. So, here we use multiple jets, which makes it faster. Binder liquid is sprayed in selected regions instead of laser. Now, this will not require sintering inside another furnace. It is written it is not required, whereas this requires sintering. Okay. Now, when binder is sprayed through thin nozzles, uh, the the particles in that region stick together. The remaining powder acts as a support. So, use of multiple that is why use of multiple jets in this printer makes it a faster process. Why this makes it a faster process? Binder is sprayed through thin nozzles. Particles in the region stick together and remaining powder acts as support. Okay, so this is the reason these are the following statements are correct. Option B and C. Next question. So which of the following functionalities are possible time delivery drug in binder based powder bed additive manufacturing process? So multi drug release we just discussed. It can be done in binder based powder bed AM methods. So that's it for today's session. So if anyone has any doubts, let's discuss, or any doubts related to your exam. So any doubts, further doubts? So today mostly this will be the last class for this session, and we did a summary session on Saturday, this Saturday 14th. We'll be uploading the video very shortly, and there discussed some important concepts from week 1 to week 3 only, as these are the most recent portions we have covered. Okay, so no doubts as of now. So all the best for your exam, and I hope you had a happy learning. I hope most of your doubts were resolved. Okay, if there are no further doubts, we'll close the session. All the best of luck. Yeah,
Thank you, ma'am.
thank you for attending. Thank you.